Hello, my name is Ryusuke Sugimoto. In my thesis work at the University of Waterloo, I developed Monte Carlo solvers for various partial differential equations. Monte Carlo methods known as ray tracing methods are used widely in rendering today due to their capabilities to offer a quick preview of the results, handle noise in geometry robustly, parallelize the computation easily, consume only a small amount of memory, and perform evaluation of the solution only where it matters. My work aimed to support these advantages when we solve PDEs. One of the works in my thesis aimed to support PDEs with many different boundary conditions. We introduced the Walken boundary method to computer graphics. This is a Monte Carlo method for PDEs, such as the Laplace equation. To estimate the solution, just like Monte Carlo ray tracing for rendering, we sample many different paths stochastically and compute their average contributions. Using a different boundary integral equation for each problem, we can estimate the solutions to Laplace equation with Dirichlet, Neumann, Robin, and mixed boundary conditions in both interior and exterior domains with Walken boundary. Additionally, the high similarity between Walken boundary and Monte Carlo ray tracing enables the use of various sampling techniques from rendering to improve the efficiency. We can also extend Walken boundary to support more advanced equations than the Laplace equation, including the time-dependent diffusion equation and the vector-valued Stokes equations which describe the flow of highly viscous fluids. Equipped with these basic solvers, I tackled much more complex, dynamic, and nonlinear Navier-Stokes equations. By applying the operator splitting method to the vorticity-based or velocity-based form of the Navier-Stokes equations, we can simulate fluids by considering the effect of each substep in sequence. Here, we can apply Monte Carlo PDE solvers to solve the substeps highlighted in dark blue. As the Monte Carlo PDE solvers can handle tiny geometries effortlessly, the fluid solvers that can utilize them can also handle such geometries without special care. In a more extreme scenario, we can handle very noisy geometries effortlessly too. Additionally, the velocity-based Monte Carlo fluid method can utilize several traditional simulation techniques, including buoyancy simulation and divergence control within the Monte Carlo framework. The last piece of my thesis work tackled the problem of solving PDEs on surfaces. The idea of our method, which we term the project at Walken spheres, was to modify the Walken spheres Monte Carlo method with an additional projection step inspired by the closest point method for surface PDEs. Our method is surface representation agnostic and can even support surfaces represented with a combination of triangle mesh, oriented points, and codimensional rods. Our method supports view-dependent evaluation as well, where the solution resolution is not directly affected by the surface geometry discretization resolution. Together, my thesis advanced the state-of-the-art of Monte Carlo PDE solvers. Thank you.
Hi, my name is Siqi Wang. I obtained my Ph.D. from New York University in 2025, advised by Daniele Ponazzo and Dennis Sorin. My thesis is titled Shape Design, Repair, and Optimization. The life cycle of digital shapes, from design to fabrication, faces challenges like redundancy, imperfection, and meeting physical objectives. We develop computational tools that automate shape design, repair, and optimization process, iterating until the shape is ready for fabrication. My thesis enhanced the pipeline with 3 parts: a simplification tool for cleaner design, a labeling method for simulation-ready meshes, and 2 optimization frameworks for textures and MRI coils. A key problem in shape design is, given a whatever dense SVG, how to simplify as much as possible while remaining accurate. We propose a new algorithm for simplifying Bezier splines with high fidelity that guarantees the smallest possible zero-error solution first. Our method outperforms Adobe Illustrator and Inkscape qualitatively and quantitatively. It can also be extended to higher dimension to generate temporal coherence SVG animations. Artists created meshes often lack well-defined interiors, causing volumetric meshing to fail. Therefore, we introduce a method that takes as input a surface mesh and assigns to each face a label determining whether it belongs to a solid or shell, so that we can generate a reasonable volumetric mesh. With only minimal user guidance, the labeling is automatically solved through an optimization process. It's useful to generate robust volumetric meshes for applications like CSG and physical simulations. The shape optimization approaches have been highly successful in material design, fluid dynamics, and structural mechanics. The last part of my thesis introduced two shape optimization frameworks. The first is for textures. In this work, we are able to control textures' tactile feeling and visual appearance independently by solving tactile and appearance optimization at the same time. It allows visually impaired users to distinguish shapes through touch while still keeping the same visual appearance. The second framework is to optimize the MRI coil arrays. In this work, we developed an entire pipeline of the MRI toolkit, aiming to improve the SNR in the target region of human body by optimizing a set of coil design parameters. As a result, we are able to improve the average SNR in the entire brain by 9% and center of the brain by 7% through shape optimization. To conclude, my thesis addresses key issues in shape simplification and volumetric meshing, providing the groundwork for two shape optimization pipelines. Thank you.
Hi everyone, I'm Shivangi and my thesis focuses on high-fidelity photorealistic avatars. The thesis makes four main contributions. Clipface enables avatar customization from text prompts. FaceTalk enhances geometric appearance of animatable avatars from spoken audio. Gaussian speech further refines these talking avatars and makes them photorealistic. Finally, scaffold avatar synthesizes ultra-high fidelity animatable avatars. Clipface introduces the first method for texture and expression editing of a 3D face model with text prompt, simplifying content creation process. We first train GAN-based model to synthesize UV textures. Then we edit these UV maps based on given text prompt with clip loss. Our method can easily interpolate between different texture styles. Finally, we show expression editing and corresponding geometric deformations. However, Clipface is limited by its coarse facial geometry, which reduces photorealism. FaceTalk takes the next step by proposing the first method to synthesize detailed 3D geometric animations from spoken audio, enabling significantly richer facial expressions.
Hello everyone, and congratulations to the class of 2020.
It uses latent diffusion in neural parametric head model space to synthesize volumetric head animations. It can synthesize realistic animations for in-the-wild audio clips.
Confidence is your best accessory.
However, it misses photorealism and can't be applied to real-time applications due to slow diffusion denoising. Gaussian speech addresses this by introducing the first real-time audio-driven textured 3D avatars. This enables photorealistic and free viewpoint animation.
Bright sunshine shimmers on the ocean.
We first initialize a lightweight avatar from 3D Gaussian splats, and then we animate it with a sequence model. Our method generalizes to various in-the-wild scenarios.
It's been a while without thinking of you, but the thought makes me smile.
However, Gaussian speech lacks fine facial details when zoomed in. Finally, Scaffold Avatar addresses this problem and proposes the first method to synthesize ultra-high fidelity avatars. The key idea of the method is to first leverage patch-based face model to obtain fine-grained localized expressions, which are then used to synthesize 3D Gaussians on the fly for efficient rendering. Here, we show fly-through of the avatar by zooming into fine-scaled facial regions, enabling micro-expression capture for cinematic quality digital humans. To summarize, my thesis presents methods for synthesizing lifelike 3D avatars. By capturing fine facial details, it brings us closer to fully photorealistic avatars.
Hi, I'm Nicole, and my thesis develops algorithms for geometric data processing and analysis. The reason why I'm interested in this area is that our lives in many ways are defined by geometry, from natural phenomena to human structures. Geometry characterizes our relationship to the physical world, often on many different levels, and our ability to solve problems involving geometry drives technological progress. In general, these geometric problems can be hard to solve, simply because we don't always have great ways of doing computation with geometry. Many operations often break down if the geometry fails to satisfy some ideal standards. This is unfortunate because there's so many ways geometry can be non-ideal, and it's hard to predict how. Further complicating matters, there are so many different types of representations, and each of these representations has their own low-level defects. All of these low-level defects are unpredictable and frustrate higher-level design and optimization tasks. So we need to be able to compute geometric quantities from defective and diverse data, and defining what this means and building algorithms towards this goal requires answering fundamental questions about geometry. In other words, we need robust geometry processing. So during my PhD, I've answered two geometric questions in a robust way, computing inside and outside and sign distance. A theme is that we gain robustness by considering smooth functions that encode geometry. And while using functions to reason about geometry isn't really a new idea, I show how using derivatives of these functions gains geometric and topological information that you couldn't have otherwise. For example, inside and outside is hard to compute on general surfaces because there might be closed curves that simply don't have a well-defined inside or outside, and these curves completely foil traditional algorithms. We show that by processing a derivative of our inside-outside function, you can properly account for ambiguous input using a duality between curves and vector fields, letting you compute the inside and outside of shapes robustly on all sorts of surfaces under all sorts of conditions. Beyond inside and outside, we further asked how to also recover distance to a well-behaved reconstruction of corrupted geometry. This means that robust sign distance itself depends on a well-defined notion of inside and outside. We show that these two quantities are actually equivalent under certain conditions, unifying decades of geometry processing algorithms. But crucially, we show that there's also a fundamental trade-off that means that you cannot simultaneously obtain good reconstruction and distance quality, at least not with scalar data alone. So once again, we process derivatives to get good distance accuracy to a good reconstruction of the true surface underlying an imperfect observation. Our resulting algorithm makes sign distance robust to curves and surfaces of varying dimensions, representations, and settings. More broadly, by strengthening operations as fundamental as inside and outside and sign distance computation, we strengthen algorithms across graphics, vision, and robotics that all depend on good geometry processing. Thanks.
Hello everyone. I want you to imagine a new kind of physical therapy. Instead of boring, repetitive exercises, what if your daily workout was fighting a dragon or meeting a unicorn and going into a vibrant park having fairies and butterflies? That's what my PhD is all about. My name is Tahmeena Javaid. I recently completed my Ph.D. under the supervision of Oleg Frenzo and Rehanzia from Bournemouth University, UK. Topic of my research is use of fantasy in serious games to assist physical rehabilitation. My work specifically focused on the back pain in physical rehabilitation. Back pain is a health issue faced by people in every part of the world. It costs countries billions. The typical fix? Simple exercises. But let's be real, they are boring, they hurt, and people quit. That's where serious games come in. The research use motion sensing technology like Connect VR headset to turn exercises into a game. But most of those games are too simple. I figured out how to make them better by adding a rich fantasy narrative and visuals. My big idea was proving that adding a magic, mythical elements and a rich story actually works better. But question here is, why fantasy? There were three main reasons behind it. One, motivation. You're not just moving your body, you are channeling energy to win a quest. This turns a dull, painful act into a heroic stuff, making people want to play more and stick with it. Second, immersion. The game is so real, so immersive that your brain focuses on the quest instead of the pain in your back. It is like digital distraction that makes the pain smaller. Third, feeling strong. Finishing a strong quest in the game, like finding the magic key, make you feel powerful in a real life too. You start thinking, if I can do that, I can definitely handle my 10 minutes of exercise. My research developed and tested a prototype serious game where specific back pain exercises validated by medical experts were implemented and directly mapped into the fantasy world. The results were compelling. Compared to the control group, using a standard non-fantasized gamified approach, the fantasy group showed significantly higher enjoyment. And the best part, they actually wish to do the exercises more often. The exciting story, element and engagement of the fantasy world kept them coming back. So my research proved that by using the power of fantasy element, a painful, boring part of rehabilitation can be fundamentally transformed. We are not just making exercises fun. I tried to help patients and find their inner hero and giving them a compelling reason to fight for their health. The future of physical therapy lies on the digital battlefield of epic wins. Thank you.
My name is Uday, and my thesis studies the computational design of umbrella meshes. Umbrella meshes are assembled in a planar, compact, stress-free state and deployed to a pre-programmed expansive state. Deployable structures transform from an easy-to-transport compact state to an expansive state. For fabrication benefits, several works focus on planar to 3D deployment. However, notice that the material is always redistributed within the surface plane. Inspired from an umbrella, our cell consists of scissor mechanisms attached between plates. Cells of different heights expand to footprints that are incompatible at the shared edge. We exploit this incompatibility to buckle out of the plane. An umbrella mesh with varying cell heights buckles out of the plane into an elastic equilibrium due to the incompatible cell footprints. We developed the simulation framework for deployment, modeling the geometry, constraints, and forces involved. For the inverse design that deploys to a given target surface, we use conformal mapping to give the topology and an initial solution. We perform numerical optimization to improve this design. Umbrella meshes have a large shape space due to their unbounded scale factors. They capture extrinsic coverage, provide structural stiffness, and offer design flexibility. We can 3D print the stress-free compact state in one piece. We also made larger models by milling the parts and assembling them. If we can reconfigure an umbrella cell by sliding the plates and locking them in a different height, it deploys to a different footprint. So the same umbrella mesh can be reconfigured to deploy to different shapes. Our physical prototype validates these results on a larger scale. Reconfigurable cells are shape agnostic and stress-free, allowing mass fabrication and easy assembly. They promote component reuse across multiple cycles as opposed to custom fabrication. Precisely optimized designs of bending active structures have bespoke custom components with different dimensions and properties. We compute an optimal kit of parts which can be used to recover the designs without sacrificing much design fidelity. While we focus on bending active structures in general, it applies to umbrella meshes too. Our framework enables analyzing trade-offs between part set size and design fidelity. It can also be used to find a kit of reconfigurable parts. To summarize, my thesis provides a comprehensive framework for design and fabrication of umbrella meshes, opening up new possibilities for discovery and optimization of novel shape morphing structures. I conclude by thanking my collaborator.
Hello, I'm Diana Marin, and I recently defended my Ph.D. at TU Wien, titled Proximity-Based Point Cloud Reconstruction. My work poses a deceptively simple question. Given disconnected samples, how can we connect them such that geometry and structure reemerge? The usual answers include the nearest neighbor graph, the minimum spanning tree, the relative neighborhood graph, the Gabriel graph, or the Delaunay triangulation. An outlier of this hierarchy, and the connecting thread of my thesis, was the Spheres of Influence graph, or SIG. First introduced by Toussaint, 2 points are connected in SIG if the distance between them is smaller than the sum of their nearest neighbors. Visually, this can be interpreted as centering a sphere at each point and growing it until it touches the nearest vertex. Then, we connect all points whose spheres intersect. In other words, SIG encodes local density without a fixed parameter. We investigated the properties of this graph and its extensions in various contexts: curve reconstruction, clustering, and data analysis. For curve reconstruction, we intersected the Delaunay triangulation, which provides clean geometry, with the spheres of influence graph that provides local density to obtain the SIGGRAPH. We proved that this graph contains the correct reconstruction under sparser constraints than state-of-the-art. With additional inflate and sculpt post-processing steps, we are able to reconstruct manifold curves in more cases than prior work. Once the curves are lifted to non-planar surfaces, and more generally to Riemannian manifolds, we also adapt our curve reconstruction method. We transform the SIGGRAPH into SIGGDV by exchanging the Delaunay triangulation for the dual Voronoi graph. We extend our theory and method to these spaces, and both analyses and experiments show that we can reconstruct with far fewer samples, reliably recovering multiple curves directly on non-planar domains. Lastly, we introduce a new proximity graph, the Stability Incorporated Neighborhood Graph, or SING. By extending the spheres of influence graph to a more flexible definition, we obtain a noise-robust structure that takes local density into account. This allows us to use topological data analysis to find meaningful clusters, while only requiring a distance semi-metric defined on the given data. From SIGGDT for curves in the plane, to SIGGDV on manifolds, to SING for clustering, the path is the same. Encode proximity well and structure follows. Through my thesis, I've shown that the seemingly small modeling choice, namely how we define proximity, scales to a big and provable impact. Thank you.
For tuning in to this Thesis Fast Forward presentation of integrable symmetric fields in computational design, from stable woven shells to seamless parametrizations, presented by Josh Vector. The motivating question of this thesis was the computational design of complex structures. While often the butt of academic jokes, weaving has been an essential part of the built environment for thousands of years, both for humans and for other species. Weaving also shows promise as a fabrication modality across length scales, from the microscopic to the human to the architectural. Given this wide range of interesting applications, the first significant project in this thesis was the development of a design pipeline for arbitrary woven shells. This pipeline took as input an arbitrary triangle mesh and then used techniques from global optimization in order to realize a set of design patterns that could be then translated into the real world. Here is an illustration of the assembly process of an icosahedral model. One key challenge we found formulating this inverse design pipeline was the placement of dislocations or darts in the weaving pattern. We made connection between dislocations in a weaving pattern and topological singularities in a vector field, and leveraged techniques from geometry processing to automatically place these singularities in our pipeline. This exploration of geometry processing led us to then study a related question of volumetric parametrization. The task of volumetric parametrization involves computing a map F from a geometric domain to a parametric domain, which is kind of like Minecraft. Given such a map F, one can then invert it in order to find a discretization of the original geometric domain into approximately cube-like regions called hexahedra. The robust computation of such a map F remains an unsolved problem in geometry processing today. State-of-the-art approaches for this task typically decompose it into two steps. The first involves a global frame field solve, akin to what we use to find the locations of darts in our inverse weaving pipeline, except in 3D, the singular points become singular curves. Given the solution to this frame field solve, we can then use it to guide a global integration step, which is then used to recover the boundary line parameterization. The trouble with this pipeline is that on complex examples, it yields poor parameterization quality. In the second significant work in this thesis, called MINT, we explore the idea of modifying the global frame field solve by adding integrable moment constraints. We find that performing the same solve with these additional constraints consistently improves parameterization quality. The key theoretical contributions of MINT are twofold. First, we introduced a novel representation of symmetric frame fields, and then we leveraged this novel representation to develop the first exact discretization of symmetric integrability in volumes by building on earlier work which discretizes vector field integrability on tetrahedral meshes. To conclude, in this thesis we developed a theoretical and computational toolkit for inverse problems ranging from inverse weaving to volumetric parameterization. Thank you for listening.
Hello everyone, my name is Jiayi Zhang and I go by Iris. I'm a 5th-year PhD student at Stanford University, advised by Professor Doug James, and I also work closely with Danny Kaufman at Adobe. My research primarily focuses on developing intelligent algorithms, models, and tools for enhancing user creativity and productivity in design, animation, and simulation. At the center of my PhD thesis is progressive simulation, a novel coarse-to-fine simulation framework and interactive system that adapts level of detail principles to achieve efficient, high-fidelity, controllable simulation at scale. As motivation, the research question I would like to address is the fundamental trade-off between simulation speed and fidelity, the dilemma that all simulation tasks face. Taking cloud simulation as an example, interactive design of high-quality cloud simulation in 3D modeling softwares should be as simple as in the real world. However, this still remains as a challenge. On the one hand, fast cloud simulation now reach interactive rates on extreme meshes, but their simplifying assumptions cap expressiveness and produce artifacts. Meanwhile, high-fidelity methods like IPC capture rich, realistic contact and wrinkling, yet remain too slow for interactive workflows. So my research asks, if fast, high-fidelity deformable physical simulation isn't currently possible, how can we faithfully capture these details while maintaining speed and interactivity? To this end, my research program generalizes and elevates the widely used LOD concept from everyday media compression like JPEGs and graphics, like in progressive refinement in rendering and geometry, into physics simulation. As a first step, we develop a progressive simulation method for efficient cloud quasi-static previews with consistent progression across resolutions, reliability, interoperability, and interactivity. To demonstrate PCS workflow, here's one application where the user manipulates clouds, gliders, and materials, and later produces a low-res draping. During process, our solver automatically improves to consistently high-res drapes while user iterates on the low-res mesh for more interactive editing. Finally, when the user is satisfied with their design, refines offline to final highest res geometry. Powered by our technique, in this still life demo, the user is trying to lay out a piece of tablecloth, and thanks to PCS robust collision handling, can move complex obstacles directly to push clouds around and between shapes. Once edits settle, PCS automatically refines to finer level solutions. When no further edits are desired, the user could just go to grab a coffee, and a few minutes later, come back for a converged, high-quality, non-intersecting result for tightly nested geometries. Going beyond quasi-statics, later we also propose progressive dynamics, a coarse-to-fine, level-of-detail animation method for complex frictionally contacting thin shell and cloth dynamics. Compared to direct simulation, which quickly diverge, progressive dynamics maintains these tightly matching results with increasing details without drifting even over long time spans of highly dynamic motion. Users can use course previews to rapidly explore the layout and various physical parameters. Once they find the configuration they like, they can just fire off progressive simulation and eventually arrive at this beautiful final result. Beyond these published works, to further extend progressive simulation in the future, we can certainly extend it to a wider variety of objects, including solids, fluids, and rods. At the same time, consider exploring multi-scale time resolution integration methods to unlock better numerical properties and parallelism, together with its GPU implementations to speed up its computation and even synthetic data generation for robot learning, so that eventually we can achieve true scalability for both virtual and real experiences. Thank you for watching.